Welcome viewers. Today's topic on kinetics of fast order reaction. Before going to the details of kinetics of fast order reaction, let me tell you what is order of reaction and molecularity of the reaction. Two terms, molecularity and order. These two words I shall explain you in details. Whenever any chemical reaction is going on, we used to write A will give rise to product B. But actually this does not happen. It moves through several steps like A changes to B, changes to C, changes to D, then to P. Out of all these steps, we have to see which one is the slowest step. Which one is the slowest step? Now, the total number of molecules taking part in the slowest step, which is also called as a rate determining step, will give its molecularity. I am repeating the line once again. Out of all these steps, the slowest step is called the rate determining step. Now in the rate determining step, the total number of molecules taking part will give its molecularity. Let us discuss what about order. Again I am repeating the words, the same words. In the rate determining step, the total number of molecules taking part and whose concentration changes will give its order. In case of molecularity, the total number of molecules which are taking part. But in case of order, the total number of molecules taking part and whose concentration changes during the process will give its order. But a better definition for order is like this. Suppose there is a reaction XA plus YB will give rise to product. Now rate is proportional to A to the power X, B to the power Y, or rate is equal to K into A to the power X, B to the power Y. The order of the reaction is defined as the sum of the exponents, I mean the power, which the reacting species are raised in the rate expression of the chemical reaction. order of the reaction is defined as the sum of the exponents. Exponent means power to which the reacting species are raised in the rate expression of the chemical reaction. So order is equal to n, that is equal to x plus y. This is the modern definition or the actual definition of order of the reaction. Now I shall tell you kinetics of first order reaction. First order reaction is that reaction where the concentration of only one molecule will change. I shall tell you some examples of first order. Nitrogen pentoxide will give rise to nitrogen pentoxide will give rise to nitrogen tetroxide, or this can be written as N2O4 plus half O2, or this is nitrogen dioxide, also called as nitrogen peroxide, and half O2. So this is one example of first order. Also, hydrogenation of ethylene in the formation of ethane is another example of first order. These are the examples of first order reaction. Now, I shall derive the rate constant for the first order reaction. Suppose there is a reaction A gives rise to product. Let this reactant A has concentration A moles per liter. The unit of concentration is moles per liter. I am telling you the substance A has concentration A moles per liter. When time t is equal to 0, A has A moles per liter and no product has been formed or nothing has been formed. After time t, X moles per liter is removed from A to give rise to product. After time t, from A, which has A moles per liter, X moles per liter has been removed for the formation of the product, and the remainder is A minus X. So X is going with respect to time t. When X is very small, t is very small, I mean they are infinitesimally small values, then we write dx by dt is proportional to a minus x, or dx by dt is equal to k into a minus x. Or dx by a minus x is equal to k dt. I can write it in this way: 1 by a minus x dx is equal to k dt. Integrating both the sides, 1 by a minus x dx, integration of k dt. So integration of 1 by a minus x dx is equal to k taking constant, k taking outside, which is a constant, integration of dt. This k is the first order rate constant, whose value I am going to derive. Now integration of 1 minus x dx, let me tell you what is its integration value. Put a minus x is equal to t. Differentiating this equation with respect to dx of a minus x, with respect to t, it will be dt by dt. Now dA by dt minus dx by dt is equal to dt by dt is 1. Differentiation of a constant quantity A is 0, so minus dx by dt is equal to 1, or dx is equal to minus dt. Now I shall put the value of dx as minus dt in this equation. I have put a minus x t, so 1 by t dx is minus dt is equal to k integration of dt. Now integration of 1 by dt minus dt is taking minus outside, integration of 1 by t dt is equal to k integration of dt. Now integration of 1 by t is ln t minus ln t, and that of k is there, dt is integration dt is t. When integration is over, I have to put one integration constant, that is c or I shall write it here as c, where c is equal to integration constant. Now putting t is equal to a minus x minus ln a minus x is equal to kt plus c. Let it be equation number 1. Students used to commit a mistake that integration of 1 by a minus x, they used to write ln a minus x. Actually, one minus symbol will come. So the value is minus ln a minus x is equal to kt plus c. Now, when t is equal to 0, nothing has gone for the formation of the product. So, x is equal to 0. Putting these two values, minus ln a minus 0 is equal to k into 0 plus c. So minus ln a is equal to c. Now we got the value of c. This value of c I am putting in equation number 1. Minus ln a minus x is equal to kt minus ln a. So the equation for a derivation of rate constant changes its shape as kt is equal to, taking ln this side, ln a minus ln a minus x, or kt is equal to ln a by a minus x. Converting ln into logarithm table which we are using in the book, kt is equal to ln a by a minus x. K is equal to 1 by t ln a by a minus x. We know ln is equal to 2.303 log. So K is equal to 2.303 log by t a by a minus x. I am writing this equation in a clear way. K is equal to 2.303 by t log of a by a minus x. This is the rate constant value for first order reaction. I shall tell you here what is half-life period and what is its relationship with rate constant. This is important from examination point of view. Half-life period is the time taken for half of the reaction to be completed. Half-life period is the time taken for half of the reaction to be completed. Life period of a reaction is 10 minutes. I should not dare to say that its half-life period is 5 minutes. This is wrong, absolutely wrong. Half-life period means the time where half of the reaction is completed. Half of the reaction is completed. It is symbolically represented by T in the subscript 1/2, or we can write it T 0.5. Half-life period is the time taken for half of the reaction to be completed. If the life period is 10 minutes, its half-life period is not 10/2. Rather, for this reaction to be half completed, whatever time it will take, that is called its half-life period. Now, putting the value here, K is equal to K is equal to 2.303. In place of T, I shall write T half log of A by A minus X. What is the value of X? Because the half of the reaction is completed. Hence, I shall not write X, rather I shall write A by 2. Now, K is equal to 2.303 by T half log of A by A minus A by 2 is A by 2. That will give me K is equal to 2.303 by T half log of A into 2 by A. 2 by A. A cancelled. So the result comes K is equal to 2.303 by T half into log of 2 into log of 2. Now the value of log 2 from the logarithm table is, you have to remember, log 2 is equal to 0.3010, log 3 is equal to 0.4771, log 4, you can find out log 4. Log 4 is log of 2 to the power 2, that is equal to 2 log 2. So the value comes 2 into 0.3010. But my point is, here the value for log 2. So K is equal to 2.303 into, for log 2 the value comes 0.3010 by T half. the final value is k is equal to, after multiplying 2.303 with 0.3010, it comes 0.6932 by t half, or half life period of t half is equal to t half is equal to 0.6932 by k. This is the value of half life period. Another term I want to use, life period, which is symbolically represented by t, and that is equal to 1 by k. Life period is the reciprocal of rate constant. It is the reciprocal of rate constant. So that is equal to 1 by, in place of k, I shall write 0.6932 by t half, or t is equal to 1 by 1 into t half by 0.6932. So t is equal to, dividing 1 by 0.6932, it comes to 1.44 into t half. This is the relationship of life period with half life period. I have taught you in details the derivation of rate constant for fast order reaction, its relationship with half life period, and the average life also. I hope you will like my teaching today. If you like, please subscribe. Thank you. Thank you all.